rank in order from smallest to largest this girl's speed at the bottom. All right. Anybody want to shout out their answer that they know is absolutely right? Think about this. All of her potential energy at the top is the same, correct? So y'all start at the same height. She has the same mass in all four situations. This is the key right here. Frictionless. Frictionless means all of the potential energy at the top here is turned to all kinetic energy down here. There is no loss of energy due to friction. There's no thermal. So, as a result, show us your answer, oh wise board.
Hey, you can't do that. I thought you were like, actually.
It's all of the potential is turned into all of the kinetic, which means, and her kinetic is her mass and her velocity. Well, it's 1/2 mass times velocity squared. Her mass doesn't change in all of these situations, so therefore her velocity must be the same in each situation. All right, maybe if we have time, we'll do a little activity in that. See if there we go. We already talked about the elastic potential energy formula, so now let's move on to here. 3 balls are thrown from a cliff with the same speed but at different angles. Which ball has the greatest speed just before it hits the ground? Now, you might say, oh, this is exactly like the slide problem. Right, Kevin? Right? All right. No, I'm glad you're with me here. Because, walk through this with me, they all have the same potential energy here. And then by the time they hit here, all of that potential energy is turned into kinetic energy. However, what is different about this situation?
The potential energy changes.
That is the same. All of the potential energy is turned into kinetic energy. There is a different angle on each one of these, okay? But in this case, we don't just have the girl sitting at the top of the slide initially. In each one of these situations, the ball also has kinetic energy. Does that make sense? So the initial is mgh. So for situation, this one right here, the ball has mgh plus 1/2 mv squared initially. And then all of that, by the time we get down here, is transferred into 1/2 mv squared. Does that make sense? It's turned into all kinetic. Up here we have potential due to gravity plus kinetic initial. Down here we just have kinetic final. What about for this for the ball when it's thrown out like that one? Does it have potential energy? Yep.
Yeah.
What about its kinetic energy? Well, that's also, so we have mgh. That is also 1/2 mass times the velocity squared. And all of that is turned into, when the ball hits right here, kinetic final. All right? Now the first question is, what's the difference between this kinetic final and that kinetic final? Well, we don't really, if we do that, then we know the answer to the question. So let's go back and see the source that they came from. Is there any difference between the kinetic and potential energy of a ball that is thrown upwards and the kinetic and potential energy of a ball that is thrown horizontally?
No.
The answer is no. The direction of the velocity does not matter when it comes to kinetic energy. The magnitude makes the difference. But look, all 3 of those vectors have the same magnitude. As a result, they all have the same initial v squared. Okay? So this one also has, ug plus k initial, which is mgh plus 1/2 mv squared. And the mass is the same in all of these. The gravitational acceleration due to gravity is the same on each case. The height is the same on each case. 1/2 is always the same on each case. The mass is the same in each case. And the initial velocity is the same. So what I have in each one of those circles for the ball in each 3 of the scenarios, it's the same. And all of what's inside that circle of initial energy gets turned into the kinetic final energy, which in each one of these cases is 1/2 mv squared. In this case, it's also all kinetic, 1/2 mv squared. In this case, 1/2 mv squared. The 1/2 is the same in each case. The m is the same in each case. Since the total kinetic energy is the same, therefore the v must also be the same in each case.
So the height in that equation is only your initial height.
That's correct.
By throwing it up, it doesn't make that change.
Good question. What will happen with this ball, if we were to have a little graph of, like, on that skate park thing, right? This is kinetic energy, this is potential. This is potential and kinetic. So this has a whole bunch of potential, and since it's being launched up here, has, I don't know, maybe about this much kinetic, right? By the time it gets to the very top, notice it still has a horizontal component. So its kinetic is down here to almost nothing because it doesn't have any vertical. However, its potential energy has increased. It's shifted. By the time it gets all the way down to here, the potential energy amount is totally zero. There's nothing in there, and it is all kinetic. It's this amount plus, it's all kinetic. Does that make sense? These questions are designed to mess with your mind, Initially, your first thought is they're all the same because it's the same, but then you're like, oh, but wait, it's throwing at different angles. And you might think that a ball which is thrown downward might be traveling faster than a ball which is being thrown upward at the same velocity. However, think about it like this. Remember when we talked about parabolic motion? What if you throw something up at 10 meters per second, okay? By the time it reaches this point right here, it is now traveling downward at 10 meters per second, which is exactly the same situation that you have there. Okay? So, all the balls have the same speed when they hit the ball. All right. So, we're rethinking all of these problems in terms of like energy before, energy after. Okay? This question says a hockey puck sliding on smooth ice at 4 meters per second comes to a 1 meter high hill. Will it make it to the top? Will it get up over here at all? Let's talk about how we set this up in terms of energy before and energy afterwards. Okay? Since it's saying smooth ice, that's going to imply to us that the change in thermal energy is zero. All the energy is going to be converted here into here. We're not going to have any thermal effects for this. So talk to me about the energy before. What sort of energy do we have here? Kinetic. Kinetic? So kinetic initial. Do we have any potential?
No.
No. What about up here? What do we have?
Potential.
We've got potential. Do we have any kinetic?
If she stops. If
Okay.
she doesn't.
If it doesn't make it all the way to the top, then it's going to stop right here, right? So, it's possible that it makes the top and keeps going. So we're not really sure what we should do about the kinetic. What I would suggest for this type of problem, since they're just saying, will it make it to the top, okay? What we can do is we can figure out what's the total kinetic energy available here, okay? And let's figure out how much energy would it have up here if it just was put up here. Like if it just barely makes it and all of that potential is turned into kinetic. Does that make sense? So here, this is just going to be mgh. Let's just figure out how much energy does it take to get up from here to here. So that's going to be, do we know how heavy this puck is?
No, that's the problem.
Oh, mgh. Okay. All right, what about, do we know this over here? And then kinetic initial. 1/2 mv squared.
We don't have enough.
We don't have the mass either, okay? But let's just say, let's just leave it as m and see what we can find out. The kinetic energy initial is 1/2 times the mass times the velocity squared. So the velocity is 4. So 16 times 1/2, so that's 8m. Its kinetic energy initial is 8m. 8 times whatever its mass is. If it is up here at the top and not moving at all, and it just has potential energy, okay, then that's going to be m, we'll round the g to 10, and a height of 1. So it's going to take 10 m to get up to the top. 10 m joules of energy, all right, to be able to get up here. Do we have 10 m available to us? No, we don't. We only have 8 m. You're like, what's the mass? We don't know the mass. You don't need to know the mass. We've got it all in terms of mass. Sorry, Puck. You're out of luck. All right, here we go. An archer pulls back the string on her bow to a distance 70 centimeters from its equilibrium position. To hold the string at this position takes a force of 140 newtons. How much elastic potential energy is stored in the bow? Gracie, what's the formula that you all started to use on this one?
US equals half kx squared.
Okay. You know the 1/2. Do you know the x? 70 centimeters. In meters, por favor. 0.7. But we need to know what that k value is.
Use the equation.
All right, yep. What is that other equation that we have at our disposal?
F equals kx.
F equals kx. This is F, I'll put SP, the force that it takes to stretch a spring or an elastic bowstring a distance x is governed by this formula here. So here we're told you've got 140 newtons, so K is 140 newtons divided by that distance, 0.7. So K equals
200.
200, the units are newtons over meters. So 200 newtons over meters. This is going to be 0.7 meters, so meter squared is 1 newton meter. And go ahead, what do we get?
49.
49 joules. Also known as, since this meter squared cancel out one of those meters, there's still a meter left of newton meters. And if you're ever not sure about the units, okay, remember that change in energy is equal to the work done, which equals the force times the distance. Force is newtons, distance is meters, so a newton meter is a joule. Not newton per meter, newton meter. All right. Y'all do you have notes on 10.5, 10.6? Okay. Let's go ahead and add on to those. Thermal energy is some of the neatest stuff here. All right. So what is thermal energy? Like, what is the temperature of something? How do we? What does that mean? What's going on? Something's hotter than something else.
If the molecules are moving faster or something.
Yeah, exactly. The molecules on the inside are moving around. Okay. So if we were to zoom in on this iron bar here, what we would see somewhat at some level if is a bunch of molecules connected through different ways that they get connected in chemistry. Sometimes it's by electron sharing, which is your molecular bonding, where they both share an electron. And sometimes one of them rips the electron from the other one, then it becomes negatively charged, and this one becomes positively charged. And so then they're attracted because of the electrostatic difference. And so you have ionic bonding, if you remember that. But we are just going to sort of gloss over all of that and say they're connected with these spring things. They're being pulled kind of, if you try to pull them farther apart, they're going to be like, nope, we're right here. If you try to push them too close together, they're like, no, we won't get that close. Okay? So they're all kind of pulling, and so they have some motion, and even something that's completely still if there is a ton of movement going on at the molecular level, all right? Not talking about like the blood going through your hand or something. I'm just talking about like even something that's dead, no electricity, just those particles they're moving around. If they weren't moving around at all, if they were just completely stationary, okay, then
0 Kelvin.
it would be at absolute zero, which is 0 degrees Kelvin. Turns out we can't actually get there, okay? We cannot get something to have it where it completely stands still. This is not the technical reason for it, but this is the way that I understand it, is like, why is it so hard to get to absolute zero? Just put it in if you try to do this, put it in a refrigerator and crank it down, right? Like, well, there's going to be some heat that's going to get inside the refrigerator from the sides, because on the outside of the refrigerator, it's like 70 degrees out here. So the air is warming up the outside, and the air is bumping into those particles and kind of heating them up, okay? And so I got the idea, just put it inside a bigger refrigerator, right? Well, what's the problem with that? It's eventually, the outermost edges are going to get, hit, and they're going to get warmed up, and then that's going to slightly warm up the stuff on the inside. So you can't ever actually get to absolute zero. At least we haven't been able to. Maybe we will figure out a way.
So
I don't
why
know.
do we watch an entire 2-hour video
I
about absolute
know.
zero in chemistry? It doesn't even exist.
It does exist. It's just we can't get
Not
there.
tangible.
Yeah. So anyway, this is kind of showing you the difference between the particles moving around in something hot where they're going bumping and jiggling and dancing, and then the ice cube, there's kind of like, it's kind of. So this is great. I think this is particularly great because I had this exact same picture in my physics book. Like I still have it. I dug it out and I look at it. I have that exact same picture. It's in your physics book and my physics book, and it's a thermal image camera shot, which we are going to get. By the way, I've got the purchase orders. Need to make that purchase. We'll look at it here in I guess probably in a couple weeks whenever it comes in. But it's an attachment. You just plug it into your iPhone or your iPad, and it shows you the heat signature of stuff. So if you drag something along the ground, you'll see this. You would see a slight discoloration, or you would see, that stretch of the carpet is a little bit warmer than this part of the carpet over here. Okay? Because the particles here have moved against the other ones. All right?
Ghost Hunter.
What's that?
Ghost Hunters.
Yeah. I went to the reason I even thought of this, I went to another teacher's class, and he had a thermal imaging camera, and the students had gone across the hall to the lab, and he just pulls it out, and we started looking around, and you could see the table where the calculators had sat, where they had because there's slightly a little bit warmer where they were, or if a kid had rested his hand on the table, and of course all the chairs were like glowing, because they sat in. If you ever sat in a warm chair, you can know the difference, So anyway, the formula for this, the change in energy is equal to the friction force times the distance. It's just force times distance. And the friction force is what's that dragging force. Okay, let's go ahead and we will implement that formula right now. This says a 0.3 kilogram block of wood is rubbed back and forth against a wood table 30 times in each direction. The block is moved 8 centimeters during each stroke and pressed against the table with a force of 22 newtons. How much thermal energy is created in this process? Okay, so I want to kind of think about what's going on. We have some sort of block of wood which is being pushed this way, then pushed that way, then pushed this way, then pushed that way, then pushed back and forth, back and forth, back and forth. 30 times in each direction. So that means a total of, you can think of it 60 times in 8 centimeters, okay? But here's what we can do. You might say, all right, that's kind of, okay, that's very logical. We're trying to heat something up or whatever. But what we can do is the same amount of thermal energy that would be generated by just going back and forth, back and forth, back and forth, would also be generated if we were to take this and just move it all the way along an entire straight line distance that's equal to that back and forth distance. So 8 centimeters is 0.08 meters, okay? We're going back and forth 30 times in each direction, so that's 60 times. So give me an actual distance here. This is our delta x. Say again?
4.8.
4.8 meters. All right. Now the friction force, which they don't tell you, it's located earlier in your book. For wood on wood, 0.2. Sorry, not the friction force, the coefficient of friction. Now, they're asking this question, how much thermal energy is involved? So, they want us to find delta E thermal. We just had an equation for that. Anybody write that down on their notes?
Thermal equals friction force times delta x.
Okay. We've got the delta x. Now let's find the friction force. So to find the friction force, I think we might need to draw a free body diagram, don't you? Yep. Well, I've got a diagram right here. It's just what forces are acting on this block of wood?
The force of the push.
Yeah. The push, they're pushing down with 22 newtons. Okay. So we've got weight, and then also this is, I'll call it like the force of the hand, right? Which is the 22 newtons. The normal, which I'm going to draw equal and opposite to both of those, okay? Because this block is neither digging into the table nor levitating above it.
Oh, the force of the hand pushing down.
Force of the hand is
Oh,
pushing
shit.
down, so that way it can move it back and forth like that. There's also the hand, I'll call this FH2. Obviously the hand is also moving it back and forth horizontally, but we really don't care about that. What we're interested in is that friction force going in the opposite direction. In fact, at one moment, the hand is pushing this way, but then whenever it turns around and gets to this point, then it's going back that way. But we'll just treat it at this particular moment right here. Now, does anybody remember a formula for friction force?
Coefficient times 1. Friction.
Yep. It's the fun formula. Friction fun. Okay, it's sort of like a puzzle here. I need to find the friction force, but in order to know the friction force, I need to know mu and n. I've got mu, it's 0.2. But what's the normal force?
So that's the mass times gravity plus 22.
Plus the 22. Yes, it's not just the weight. It's because if you think of just the free body diagram, weight and the 22 are pushing down, the normal forces combined. If you want to write Newton's second law in the y direction, you can do that as well. But the weight is 0.3 times g, which is gravity. I'm just going to round up to 10 for simplicity, so 3 newtons. So 3 newtons going down, 22 newtons going down, that's 25 going down. That means the normal force must be 25 going up. So 0.2 times 25 is 5. You're thinking 0.5.
Yeah.
All right, so now we've got something 5 newtons times the delta x, 4.8 meters. Delta thermal, 24 Newton meters or
Joules.
joules. All right. That's about all we're going to do with that friction force problem. Any questions? Oh, there's a nice free body diagram that kind of looks a little bit better. All right, yeah, we're not going to do that. All right, so here they're finally going to get around, this is 10.6, and we're just going to solve problems for the rest of class that deals with this. And that is what we've been talking about the whole time. Initial energy of the system plus the change equals the final energy of the system, okay? And that's where, now, for whatever reason, your book likes to throw it around in a different direction. They say the final plus the change is equal to the initial. I don't think that makes sense at all to me. It's the initial plus the change equals the final. This is just going to lead to a negative change. Okay? You want to think about the system, and even when you see this on the quizzes and tests and stuff like that, they're going to say something like, what is the total energy of the ball Earth system? Okay, don't get weirded out by the word that has the phrase system and stuff like that. It's just saying, don't take into account the moon, gravitational pull of the moon, and other things like that. We're just considering the ball and the Earth, or they might say the Earth box ramp system. All right, or the spring system, or something like that. All right, so here's a nice little like a Nerf gun type thing, or a pellet gun, airsoft kind of thing. Although this is spring loaded, so it's not shooting with air. Spring loaded gun shoots a plastic ball with a launch speed of 2 meters per second. Then, if the spring is compressed twice as far, the launch speed will be, oh man, maybe, might be 4, might be, I mean, are there some of those you can absolutely rule out? Yeah, it's not going to go slower. If you've got that spring, you compress it normal, and it goes to 2 meters per second, then you compress it twice as far.
And 2.8.
So, why would you cancel out C?
I don't have much reason except for that it doesn't seem logical to me.
The 2.8?
Yeah.
Alright.
Compared to twice as far, just get
Twice.
random.
Yeah.
And not very big.
2.8, yeah. Okay. The 2.8 is actually, that's being multiplied by the square root of 2. Is what's going on with that one. So, if you remember, yeah, the square root of 2 is 1.4. And so that's what's going on with this one. Alright. Let's go ahead and think about this. This is a great problem because we've got the, let's think about the energy transformation that goes on here. What sort of energy turns into what sort of energy?
Potential turns to kinetic.
Okay. What type of potential?
Elastic.
Elastic. So in the normal situation, that is the first one, we have elastic potential or spring potential energy turns into all kinetic. And so we have what is that? 1/2 k x squared turns into 1/2 m v squared. What about in the situation where we've overclocked it, or we've modded it? You can mod Nerf guns, things like that?
Yeah.
Yeah. Okay, so we'll say modded. 2 Ds?
Yes.
2 Ds, modded. Alright, so this is the modded one. What energy turns into what energy? Same thing? That's what she says. It's still spring potential energy turns into kinetic. However, what is different?
It's 2x squared.
Yes, it's going to be 1/2 k, and then I'm going to write 2x squared, and that turns into 1/2. The mass of the ball is still the same, but I'm going to put v prime squared because that's going to be different. And that's what we're interested in. What's the difference there? Okay. So one thing that we can think about, and there's different ways of solving this. One that I might do is I say, okay, when this gets squared, I still have 1/2 k, but that 2x squared turns into 4x squared, right? All right. And so that means that I can, what the neat thing is I can turn this 4 and I can pull that 4 on the outside, and I have 1/2 k x squared. That is, this is the same amount of energy that we had over in that situation. Okay? So we have 4 times as much energy available to us. Making sense? So now, what are you thinking? 16? Possibly? Okay? Let's see if you're right. So let's see if that equals 1/2 mass, and instead of putting V, I'm going to write 16 V.
What did you do? 2? Since that's the initial. No, the speed up there is 2 meters per second.
Oh, okay.
What would you plug in then?
Oh well, good question. I'm just leaving the velocity. I'm not even plugging in numbers for the velocity.
So what you? Oh, you did 16. Okay.
I'm saying 16
Yeah.
times whatever. If V is the original speed here, I'm saying that it's 16 times whatever. Okay. Let's see if that happens. Now, when I square this, okay. Oh, I see what you're saying. Hold on. This is. Okay. Yeah. Well, this is clearly not going to be right. Putting the 16 times the original V. Yeah. What I need to think is, what's the, because that's going to give me 256 as a multiplier here. If I do all this, 16 squared is 256 times 1/2 mv squared. There's no way that 4 times the original thing is equal to 256 times that thing. Okay? What you can think about it as is, what's the relationship between, from the original of 2 and the 16? It's a multiplier of 8, right? So, sorry, should we put an 8b right there? Alright, now, what's 8 squared?
64.
So I've got 64 times 1/2 mv squared. So notice I have 4 times the original energy, 1/2 kx squared, equals 16 times 1/2 mv squared? No, that's not correct. Because I have, it's sort of like I have 1/2 kx squared equals 1/2 mv squared, and I have multiplied by 4 on that side and multiplied by 64 on this side. That's not going to work. Okay, so let's try multiplying it instead of 8b. Let's put it as 2v.
Where do you get the 8 from?
They're suggesting that it was a 16, and so that would be a multiplier of 8 times the original velocity. Alright, now 2v quantity squared is going to be 4 times 1/2 mv squared. Now you can see that we've got a multiplier on both sides of 4. Okay? And so that's working out properly. They're doing with the springs. So here we go. So the idea here is that this velocity is twice what that velocity was. Which one of those is twice the original? 4. I don't know, Harley, you're giving me some strange looks over there.
Oh no, I was just trying to figure out nothing.
Okay, that's fine.
I was just thinking.
Would you like me to show you a different way on how to do this?
No, I mean, I understand what you did and how it was all worked out. I understand it. It's just,
I want to show you another way. This is one way that I think I showed y'all at the beginning of the school year, and that is to solve this expression in terms of v. Okay? See, we have 1/2 kx squared equals 1/2 mv squared. We could say, let's solve for v in terms of all that other stuff. And you end up with v squared equals, divide both sides by 1/2, it goes away. Divide both sides by m, you get kx squared over m. Or v squared equals v equals square root of kx over m. Then in the new situation, we have 1/2 k 2x squared equals 1/2 m v prime squared. So this is going to be, divide both sides by the 1/2 and those go away. You end up with 4kx squared divided by m equals v prime squared. V prime is the square root of all this. So the square root of 4k x squared over m. Your mathematics says you can separate, you can pull out the 4, so it's 2 times the square root of k x squared over m. So the new version is 2 times the old version.
Which would be 2 times 2.
Does that make sense? That's another way. So you write the whole original equation and then you write the second one. Okay. This next problem is so much like it, we're going to skip it right now. Let's think about this last problem here. It says a car sits at rest at the top of a hill. Small push sends it rolling down the hill. After its height is dropped by 5 meters, it's moving at a good clip. Write down the equation for the conservation of energy, noting the choice of system, the initial and final states, and what energy transformation has taken place. Okay?
Potential to kinetic.
Okay. Yeah, we've
And
got.
thermal.
We do have some sort of boxcar up here. After it's gone down 5 meters, it's now right here. Initially it had potential. Now it has
Kinetic and thermal.
kinetic, and there has also, we wouldn't necessarily say that there has been thermal here, but there has been a change in the thermal energy of the car ramp world system. Okay? So we have UG turns into K plus the thermal.
Why would it be the whole system thermal instead of just the car? Because at the beginning there was no thermal systems.
Right, well,
Whereas-
as the car has moved down the ramp, now,
It's progressively changed from 0 and
Yeah,
increased.
that's thermal. But why is the whole system thermal instead of just that?
I don't know what you mean, the
But-
whole system.
you
The
said-
thermal is happening between the car and the ground,
Mhm.
so the ground has to be part of the system. So you can't just take that one instant. So
Okay.
you're talking about the change in the thermal, not just the thermal at the moment.
Right.
Okay.
Some of the potential energy turns into kinetic, some of it turns into heating up these little particles along here, okay? And so since these guys end up getting affected, I have to declare that the
The whole
system is
thing.
the car and the ramp.
I thought it was just like that part. But
Yeah, no, that's, just the car in isolation is when you've got your, free body diagram. You need to have notes on 10.7 and 10.8 ready on Monday. 10.7, 10.8.